I will do now additional problems on Gauss law in integral form as well as in point form. The problem is, if vector d equals 0.1 r ar cap for r less than 0.4, 0.0064 by r square into ar cap for r greater than equal to 0.4, unit is coulombs per meter square. Find rho v at r equal to 0.2 meters and r equal to 0.5 meters. What point charge could be placed at the origin to cause vector d to be 0 for r greater or equal to 0.4? So we solve this problem. Coefficient of ar cap is what? Dr. Gauss law in point form is, Gauss law in point form is divergence of d is equal to rho v. We have been given the problem in a spherical coordinate system because r appears in the expression for vector d. This implies rho v is equal to 1 by r square dou by dou r operating on r square into dr plus 1 by r sin theta dou by dou theta operating on d theta into sin theta plus 1 by r sin theta dou by dou phi operating on d phi. In this case, here d theta is 0. Here d theta equals 0. D phi equals 0. Dr is what? Dr is equal to 0.1 into r for r less than 0.4 from here. 0.0064 divided by r square for r greater than or equal to 0.4. So what is rho v now? Hence rho v is equal to 1 by r square, expression for rho v 1 by r square. Hence rho v is equal to 1 by r square into dou by dou r operating on r square into what is dr? Dr is 0.1 r. This is for r less than 0.4. So differentiate this. So you get 1 by r square into 0.1. R square into 0.1. R cube, if you differentiate, you get 3r square. So this is 0.3 times. This is 0.3. R cube, if you differentiate, you get 3r square. R square cancels. 0.1 into 3 is 0.3. So many coulombs per meter cube. This is the value of rho v when r is less than 0.4. When r is greater than 0.4, then what happens is, when r is greater than 0.4, rho v is what? 1 by r square dou by dou r operating on what is the r square into what is dr? Dr is 0.0064 divided by r square. R square cancels. If you differentiate a constant with respect to r, it is 0. Hence, this is the expression for r greater or equal to 0.4 meter. Hence, rho v at r is equal to 0.2 meters. R is equal to 0.2 meters is what? Is 0.3. And rho v at r is equal to what is the value of r? 0.5. At r is equal to 0.5 meters is 0. How did you get this expression? This answer is valid for r less than 0.4. So 0.2 is definitely less than 0.4. Therefore the answer is 0.3 coulombs per meter cube. R equals 0.5 means it is greater than 0.4. Therefore the answer is 0. We have answered part A of the problem. Now we'll go to part B. We'll go to part B. The electric flux density due to Q is vector D is equal to Q divided by 4 pi r square into AR cap. Here r is greater or equal to 0.4 meters. Yes, told r is greater or equal to 0.4 meters. What is vector D total? What is vector D total? Vector D total is equal to Q divided by 4 pi r square AR cap plus r greater or equal to 0.4 means this is the expression for vector D. What it is? 0.0064 divided by r square into AR cap. This expression I have taken from here. Here only magnitude is written. Here I have written magnitude with the unit vector. This is the field. This is the electric flux density due to point charge. It is given in the problem. It is given in the problem. It is given in the problem. Vector D total equal to 0. Hence Q divided by 4 pi r square AR cap plus 0.0064 r square into AR cap is equal to 0. This implies Q divided by 4 pi plus 0.06064 is equal to 0. R square we can remove, AR cap we can remove. This implies Q is equal to minus 0.08043 coulombs. This is the answer. The second part is slightly difficult. You have to find electric flux density due to point charge. To that you have to add vector D given in the problem for r greater or equal to 0.4. This is the electric flux density due to point charge. This is vector D given in the problem for r greater or equal to 0.4. Then equate this to 0. From there you find what is the expression for Q. This is the answer. Thank you. We'll go to next problem. If vector D is equal to phi r sin square theta cos square phi AR cap, evaluate both sides of the divergence theorem for the region r less than or equal to 2. Solution. The problem is given in a spherical coordinate system. The mathematical statement of divergence theorem is closed surface integral vector D dot ds is equal to volume integral divergence of D dv. Call this as equation 1. To find left hand side of equation 1. Closed surface integral vector D dot ds is equal to, in the present problem, what is dr? Dr is equal to coefficient of AR cap, which is 5 times r sin square theta cos square phi. What is d theta? D theta is 0. What is d phi? D phi is 0. 5r sin square theta cos square phi. D theta is 0. D phi is 0. So, what is vector D? Vector D is what? Surface integral is always a double integral. Vector D is what? dr into AR cap. What unit vector vector D has? Vector ds also must have the same unit vector. So it is dsr into ar cap. Er cap dot ar cap is 1. So this is double integral. What is dr? Dr is 5r sine square theta cos square phi into. What is dsr? DSR is what? DL2 into DL3. So it is r square sine theta d theta d phi. Theta takes values from 0 to pi. Phi takes values from 0 to 2 pi. It is for the region r less than or equal to 2. Therefore, this has to be evaluated at r equal to 2. So, you get 5 into r is r square is r cube. If you put 2, you get 2 cube. You get 2 cube. Integral 0 to pi sine cube theta d theta. Integration phi is equal to 0 to 2 pi cos square phi. Cos square phi is 1 plus cos 2 phi divided by 2 d phi. I made use of the expression cos square phi is 1 plus cos 2 phi by 2. This is a standard integral. So this is 5 into 2 cube is 8. Sin the standard integral gives a value 4 by 3. Please remember this value. This comes even in antenna engineering. Integral 0 to pi sin cube theta d theta is 4 by 3 into half. If you integrate it 1 with respect to phi, you get 5. Sin cos 2 phi, if you integrate, you get sin 2 phi divided by 2 between 0 and 2 pi. So this is 5 into 8 into 4 by 3 into half into 2 pi. Sin 4 pi is 0. So if you evaluate this, you get the answer 167.552. 167.552 coulombs. Because closed surface integral of d dot ds is flux, therefore the unit is coulombs. So I evaluated left hand side of equation 1. Then I evaluate right hand side of equation 1. To evaluate right hand side of equation 1. First, we calculate divergence of D. Divergence of vector D is equal to 1 by r square dou by dou r square into dr. The other two terms are not required because d theta and d phi are 0. So equals 1 by r square. I don't write the other two terms because d theta and d phi are 0. 1 by r square dou by dou r operating on. Substitute dr over here. So you get 5 times r cube sine square theta cos square phi. So this becomes now 1 by r square 5 sine square theta cos square phi are constants. R cube, if you differentiate, you get 3r square. R square cancels. So you get 15 sine square theta cos square phi. This is the expression for divergence of D. So what is right hand side of equation 1? Volume integral divergence of D dV. So volume integral is a triple integral. R varies from 0 to 2. Theta varies from 0 to pi. Phi varies from 0 to 2 pi. What is divergence of D? 15 sine square theta cos square phi. What is the expression for dV in spherical coordinates? It is r square sine theta dr d theta d phi. Now integrate this. This implies right hand side is equal to 15 is a constant. R square, if you integrate, you get R cube by 3 between 0 and 2 into integral 0 to pi sine square theta d theta, integral 0 to pi sine cube theta d theta, sine square theta into sine theta, 0 to pi cos square phi d phi. So this is 15 into 2 cube by 3. This is 4 by 3 standard expression. Cos square phi you write as what? 1 plus cos 2 phi by 2. 1 plus cos 2 phi d phi, like we did earlier.
0 to 2 pi.
0 to 2 pi. Thank you. 0 to 2 pi. So this is 15 into 8 by 3 into 4 by 3 into half. If you integrate 1 with respect to phi, you get phi. Sin cos 2 phi, if you integrate, you get sin 2 phi divided by 2, limits from 0 to 2 pi. So this is 15 into 8 by 3 into 4 by 3 into half into 2 pi. Lower limit will give 0 result. If phi will be replaced by 2 pi, here you get sin 4 pi is 0. So many coulombs, same as before. So same as before. Therefore, divergence theorem is verified. We shall continue the topic with next problem. Two concentric spherical shells. This problem is on Gauss law in integral form. Two concentric spherical shells of radii R1 and R2 have charges Q1 and Q2 on their surfaces. Find vector E everywhere. Solution. We have got two concentric spherical shells of radii R1 and R2. Of radii R1 and R2. Radii R1 and R2. Inner one is positively charged to Q1. Outer one contains the charges totaling to Q2. The inner sphere, inner concentric spherical shell has charges totaling to Q1. Okay. Now we have to find electric field intensity at different values of R. First I will take the case R less than R1. This is the Gaussian surface of radius is equal to small r. What is the flux coming out of this Gaussian surface? 0. Because Gaussian surface does not enclose any charges, psi equal to 0. Hence vector D is equal to 0 and vector E is equal to 0. Construct a Gaussian surface. Construct a Gaussian surface. This dotted one is the Gaussian surface. The dotted sphere is the Gaussian surface. Construct a Gaussian surface which is a sphere of radius is equal to r. The net electric flux coming out of the Gaussian surface, is psi is equal to charge enclosed. What is the charge enclosed? Charge enclosed is 0. Since psi equals 0, it implies vector D and vector E are 0 for R less than R1. For R less than R1, there is no electric field intensity nor there is electric flux density. I'll go to second case. Second case, R less than, greater than R1 less than R2. This is second case. Case number 2. We draw two concentric spherical shells having the radii R1 and R2. Inner spherical shell has radius R1, outer one has got radius R2. The total charges on the surface of the inner shell is Q1. Total charges residing on the surface of outer spherical shell is Q2. Now, this is the Gaussian sphere. The radius of this Gaussian sphere is what? R. Is R. This is the point of interest. P is the point of interest. Point of interest is at a distance R because the radius of the Gaussian surface is R. Gaussian surface. Step 1. Electric flux. Step 1. Electric flux psi coming out of the Gaussian surface. GS is the abbreviation for Gaussian surface. Is psi is equal to charge enclosed. What the charge enclosed? Charge enclosed is Q1. If we assume that these are the flux lines coming out of the Gaussian surface, vector D is in the radial direction given by dr into er cap. Vector D is assumed to be in the radial direction and has a magnitude dr, direction specified by the unit vector er cap. Second step, to find electric flux density. To find electric flux density at point P. At point P. We know that psi is equal to closed surface integral vector d dot ds. Here S is the closed surface, which is nothing but the Gaussian surface, shown in the red color. So this implies psi is equal to double integral vector d is what? dr into er cap. What is vector ds? dsr into er cap. Whatever unit vector d has, same unit vector ds must have, so that the dot product is not 0. Er cap dot er cap is 1. dr is taken outside because it has same value or constant value at all points on the Gaussian surface. The red one represents the Gaussian surface. Double integral. What is dsr? dsr is what? R square sine theta d theta d phi. Nothing but dl2 into dl3. Theta takes values from 0 to pi. Phi takes values from 0 to 2 pi. So this is nothing but dr into r square. Sin theta, if you integrate, you get minus cos theta. Limits from 0 to pi. D phi, if you integrate, you get phi between 0 and 2 pi. This gives dr into 4 pi r square. This gives psi is equal to dr into 4 pi r square. Hence, what is dr? dr is equal to psi from this expression by 4 pi r square. What is psi? What is psi from step number 1? It is nothing but q1. q1 by 4 pi r square. So many coulombs per meter square. This implies vector d is equal to dr into ar cap is equal to q1 by 4 pi epsilon into r square into ar cap coulombs per meter square. Third step, to find vector E. Vector E at point P. This is step number 3. For case number 2, we know that vector D is equal to epsilon into vector E. This implies epsilon is equal to vector D divided by vector E is equal to vector D divided by epsilon. That means, sorry, here epsilon is not there. So it is Q1 divided by 4 pi epsilon r square into AR cap. So many volts per meter. Coefficient of AR cap is ER. Hence, ER is equal to Q1 by 4 pi epsilon r square. So many volts per meter. ER at R is equal to R1. At R is equal to R1 is equal to what? R is equal to R1 is what? Q1 by 4 pi epsilon R1 square. ER at R is equal to R2 is what? Q1 by 4 pi epsilon R2 square. So I have put in this expression small r equal to R1 and small r equal to R2. So these are the two expressions. So case 2 is complete now. Now we proceed to case 3. Case number 3. R greater than R2. So again we draw the concentric spherical shell system. The inner spherical shell has a radius R1, outer one has radius R2. Total charges residing on the inner spherical shell is Q1. Total charges residing on the surface of the outer shell is Q2. Now the Gaussian surface has got a radius equal to R. Radius equal to R. The dotted one refers to Gaussian surface. This is the point of interest, which is P. This is vector D equal to what? dr into AR cap. Again vector D is a radial direction, means along the direction of R. These are the electric flux lines coming out of the Gaussian surface. In case 3, step 1. According to Gauss law, electric flux psi is equal to Q enclosed. What is charge enclosed now? Charge enclosed by the Gaussian sphere is what? Q1 plus Q2. Q1 plus Q2 coulombs. Second step, to find vector D at point P. From case 2, we have found that vector D is equal to vector D. From case number 2, we know that vector D is equal to psi divided by 4 pi r square into AR cap. But here, what is psi? Here psi is Q1 plus Q2. Q1 plus Q2 divided by 4 pi r square into AR cap. So many coulombs per meter square. This expression, for this expression refer case 2, step number 2. Step number 3, to find vector E at point P. At point P. We know that vector D is equal to epsilon into vector E. Hence, vector E is equal to Q1 plus Q2 divided by 4 pi epsilon r square into AR cap volts per meter. Coefficient of AR cap is ER. This implies ER is equal to Q1 plus Q2 divided by 4 pi epsilon into R square. So many volts per meter. This in turn implies ER at r is equal to r2. At r equal to r2 is q1 plus q2 divided by 4 pi epsilon r2 square. R2 square. This is how we have found electric field intensity for r less than r1, for small r lying between r1 and r2, for small r greater than r2. Now I will make a sketch of it. I will make a sketch of the variation of electric field intensity with respect to radial distance. With respect to radial distance. Along y-axis we take ER. Along x-axis we take radial distance. This line is drawn at r equal to r1. At r1. This line is drawn at r is equal to r2. From the analysis we have done, we have seen that for r less than r1, this region is r less than r1. This region is r lying between r1 and r2. This region is r greater than r2. For r less than r1, electric field intensity is 0. Next, for r between r1 and r2, what is the variation of electric field intensity? We have shown that the result is q1 by 4 pi r square. When r equal to r1, what is the value? When r equal to r1, the value is q1 divided by 4 pi epsilon r1 square. From 0, suddenly it jumps to a value q1 by 4 pi epsilon r square. Between r1 and r2, it falls in the form of inverse square law given by q1 by 4 pi epsilon r square. At r equal to r2, what is the value? We have found this value as q2 divided by 4 pi epsilon r2 square. In step number 3, in case number 3, we have found that at r equal to r2, electric field intensity jumps to a new value which is q1 plus q2 divided by 4 pi epsilon r2 square. It jumps from this to a new value abruptly given by q1 plus q2 by 4 pi epsilon r2 square. For r greater than r2, it falls in the form of inverse square law. The equation of this curve is q1 plus q2 divided by 4 pi epsilon r square. This is the expression for electric field intensity for r greater than r2. This is the expression for electric field intensity for r lying between r1 and r2. What is important here is the variation of ER with respect to r is multi-valued. Means at r equal to r1, ER has got two values. One is 0, the other one is q1 by 4 pi epsilon r1 square. At r equal to r2, ER also is double valued. It has two values, namely q2 by 4 pi epsilon r2 square and q1 plus q2 divided by 4 pi epsilon r2 square. It's a very, very important problem, please. Sorry, I had written this as q2, but it is actually q1. Okay, this is the variation of electric field intensity ER with respect to radial distance. Very important problem. Please go through. Not easy if you encounter that for the first time in the examination. We shall go to the next problem. This is also on Gaussian integral form. A charge of plus q coulombs is uniformly distributed in a sphere of radius equal to r. Find vector E everywhere. Solution. So we have got a sphere. This is an insulating sphere of radius equal to r. Charges are uniformly distributed inside this sphere. What is the charge? What is the total charge Q? Q is uniformly distributed. In the previous problem, charges were residing on the surface, maybe because the sphere was a conducting sphere. Here it's an insulating sphere. So case 1, R less than capital R. I'll consider a Gaussian surface. Is the Gaussian surface of radius is equal to R. This is the point of interest P. If you keep 1 coulomb charge at point, it will be repelled in the radial direction. Therefore, vector D is outward in the radial direction and given by vector D is equal to dr into r cap. These are the flux lines coming out of the Gaussian surface. Construct a Gaussian surface which is a sphere of radius equal to r as shown in the figure. Step number 1. According to Gauss law, electric flux psi is equal to charge enclosed. What is the charge enclosed? See, q coulombs is uniformly distributed inside the volume. What is the charge per unit volume? It is q divided by 4 by 3 pi r cube. This is the charge per unit volume. So what is the charge within this volume? So multiply this by volume of the Gaussian sphere, which is 4 by 3 pi r cube. Rule of 3. Cost of 10 mangoes, 10 rupees. What is cost of 5 mangoes? 10 by 10 into 5. 10 by 10 into 5. What? Again repeat. Q coulombs uniformly distributed in the entire volume. So what is the charge per unit volume? Q by 4 by 3 pi r cube. This is charge for 1 meter cube. So what is the charge within this dotted sphere? Multiply by this by the volume of the dotted sphere. So we get this as Q into r cube divided by r cube coulombs. This is the charge enclosed by the Gaussian surface, which is a sphere of radius equal to r. Step number 2. To find vector D at point P. We know that psi is equal to closed surface integral vector D dot ds. This is nothing but double integral. What is vector D? dr into ar cap dot dsr into ar cap equals double integral dr ar cap dot ar cap is 1. What is dsr? It is r square sin theta d theta d phi. Theta varies from 0 to pi, phi varies from 0 to 2 pi. If you perform this integration, you get the result dr into 4 pi r square. Hence, see, dr into r square you take out. Sin theta, if you integrate, you get minus cos theta. If you put the limit 0 and pi, you will get 2. D phi, if you integrate, you get 5. Put limits, you get 2 pi. Okay. Hence, dr is equal to psi divided by 4 pi r square. What is psi from step number 1? Q into r cube divided by r cube is psi from step number 1 into 1 over 4 pi r square. This gives us Q divided by 4 pi r cube into r. So many coulombs per meter square. Hence vector D is equal to dr into ar cap is equal to Q divided by 4 pi r cube into r into ar cap. So many coulombs per meter square. This is the expression for electric flux density at point P, which is radially outward. Step number 3. To find electric field intensity at point P. We know that vector D is equal to epsilon into vector E. This implies vector E is equal to vector D divided by epsilon is equal to Q divided by 4 pi epsilon R cube into R into ER cap. So many volts per meter. This implies ER is coefficient of ER cap, which is Q into R divided by 4 pi epsilon R cube. This is the expression for ER, which I'll write down here. This will be required for my reference. So ER is equal to Q divided by 4 pi epsilon R cube into R. This is for R less than capital R. When correct, therefore ER when small r equal to capital R, that means on the surface of the sphere. If you replace small r by capital R, you get Q into R by 4 pi epsilon R cube is equal to Q divided by 4 pi epsilon R square. So many volts per meter. Units carry marks in field theory. Please don't miss any units. For all the expressions, dimensions or the units you must write. Units you must write. Whether it is coulombs, microcoulombs, nanocoulombs, newtons, micronewtons, millinewtons, whatever it is. Volts per meter, everything must be written. Next case. This is the sphere of radius equal to r. The total charge carried distributed inside this sphere is q coulombs. Now this is the Gaussian surface. This is the Gaussian surface, abbreviated as GS. These are the flux lines coming out of the Gaussian surface. Radius of the Gaussian surface is r. So case 2, r greater than capital R. Even though it is greater than capital R, I will put small r equal to capital R also and see what happens. This is the point of interest. Vector D is directed radially outward. Vector D is equal to dr into ER cap. Step number 1. According to Gauss law. Step number 1. According to Gauss law, electric flux psi is equal to Q enclosed. Q enclosed is complete plus Q. In the previous case, it was a fraction of Q. Here, complete Q is enclosed. Coulombs. Second step, to find vector D at point P. We know that psi is equal to closed surface integral vector D dot ds. This implies psi is equal to double integral theta varying from 0 to pi, phi varying from 0 to 2 pi. Vector D is what? dr into ER cap dot. What is vector ds? R square sine theta d theta d phi into ER cap. In fact, this is the expression for DSR. ER cap dot AR cap is 1. Correct? So you get dr into r square is constant. Sine theta, if you integrate, you get minus cos theta. Limits from 0 to pi. D phi, if you integrate, you get phi between 0 and 2 pi. So this is nothing but dr into 4 pi r square. Hence, dr is equal to psi divided by 4 pi r square. What is psi? From step number 1, psi is Q. Q divided by 4 pi r square coulombs per meter square. This implies vector D is equal to dr into ar cap is equal to q divided by 4 pi r square into ar cap, so many coulombs per meter square. Step number 3. To find vector E at point P. What is vector E? Vector E is equal to vector D by epsilon equals Q divided by 4 pi epsilon into R square into AR cap. So many volts per meter. Coefficient of AR cap is ER. This implies ER is equal to Q divided by 4 pi epsilon R square. So many volts per meter. So for my reference, I write down ER is equal to Q divided by 4 pi epsilon R square. This is for R greater than R. If you replace small r by capital R, what happens? This implies ER. If you replace small r by capital R, point P will lie on the sphere of radius equal to capital R. You get what? Q divided by 4 pi epsilon R square volts per meter. In this expression, if you put small r equal to capital R, or in this expression, if you replace small r by capital R, you get the same expression given by Q by 4 pi epsilon R square. Next, I am going to make this sketch how ER varies with respect to radial distance small r. On y-axis, I'll write ER. On x-axis, I'll write R. This dotted line is drawn at small r equal to capital R. Please note that to the left of this line, small r is less than capital R. The right of this line, small r is greater than capital R. You look at this equation. This equation is like y equal to mx. What is y? ER. What is x? Small r. What is m? Q by 4 pi epsilon r cube. Therefore, the variation is a straight line variation. What is equation of this line? Equation of the straight line is ER is equal to Q divided by 4 pi epsilon r cube. Electric field intensity assumes a maximum value on the surface of the sphere. What is that value? Q by 4 pi epsilon Q by 4 pi r cube into r. 4 pi Q by 4 pi epsilon r square. In this expression, if you replace small r by capital R, this is the expression you get. For small r greater than capital R, this is the expression. It falls off in the form of inverse square law. But however, in this expression also, if you replace small r by capital R, you get this expression, this value only. Equation of this curve is ER is equal to Q divided by 4 pi epsilon r square. As r tends to infinity, ER tends to 0. This is the variation of ER with respect to R for a sphere in which charges are uniformly distributed. Thank you.